All right, optimization. So everything that you've ever heard of about how useful math is, this is one of the most, one of the greatest uses of mathematics is optimization. Whenever you're trying to find a maximum or minimum, if you're trying to maximize something or minimize something, calculus is perfect for that. Okay, you want to maximize your profits. You have equations to describe your costs and describe your revenue. What's my maximum profit? One of your homework problems says prove the best you could do was break even. You do it using maximizing. Show that your maximum profit would be 0. That's breaking even. Then you can do that. What is the maximum population that this area can hold? Okay, what is the minimum before things will collapse? That's one of the biggest uses of calculus that is applied to not just physics, but to everything. If you can come up with an equation that describes something, you can find where its maximums and minimums are. And how do you find the max and min? Take the derivative, set it equal to 0, find the critical point, and test it. That's what you do. Okay? So, our first example. And not all of the examples here are ones that you can see as being useful, but there's a couple of them in there that are. But in your homework problems, I try to pick homework problems where you can see where a good application, a good real-world application comes up in your homework problems, a lot of them. Okay, so what is the largest possible area for a rectangle whose perimeter is 8 meters? So, what am I trying to maximize? Area. So what I need to do is I need to come up with an equation for the area using my other information. Okay, so I have to do it coming up with using my other information. So I can't use length times width, because when I want to take the derivative, I have to be able to do it with one variable. So I want to have my area written in terms of x only. So if this side is x, that side is x. What are my other two sides? And this is where it gets confusing, or this is where you have to be careful. I shouldn't say it gets confusing, because you're using your perimeter, right? So what is the length in terms of x? Well, there's two ways to do this. Well, not x plus, not, because here's what you want to think about it as. If we're doing it this way, it's 8 meters is the whole thing, right? So if I look at this way, let's call this temporarily y. Do 8 for the perimeter equals 2x plus 2y, and I want to solve y in terms of x. Divide everything by 2. 4 equals x plus y. Subtract x. 4 minus x is equal to y. Does that make sense? Do you see what I did? The whole perimeter is 8. 2 times the width, 2 times the length gives me my perimeter. Divide everything by 2, subtract x. So this is 4 minus x. So what is my area? My area equals x times 4 minus x. Do yourself a favor. Multiply it out. 4x minus x squared. What are we trying to maximize again? Area. To find the maximum, we take the derivative, set it equal to 0. To find our critical point where the maximum might be. So I do a prime, 4 minus 2x. Set it equal to 0. So x will be 2. Okay. So what are the dimensions? It says what is the largest possible area? The perimeter is 8 meters. Well, my dimensions, actually makes it easier if I put in my dimensions. So that side's 2. What's this length down here going to be? 4 minus 2, which is 2. So my area would be 4, which makes sense, because what is the maximum area for a given perimeter? If it's a rectangular shape, it's a square. If I have no limit on the shape, what is the maximum area to perimeter ratio ever always going to be? What shape? Circle. Circle always gets us our best perimeter to area relationship. If it's not a circle, you want to go equilateral. That's the second one, is anything equilateral. So if it's 4-sided, you want a square. If it's 3-sided, it's an equilateral triangle. That gives you your best ratio of perimeter to area. Okay. So, example number 2. A rectangle has its base on the x-axis and its upper 2 vertices on the parabola 6 minus x squared. First thing you want to do is you want to kind of sketch the parabola in. Well, our y-intercept is going to be 6. Our x-intercept is going to be plus and minus the square root of 6. Somebody who has their calculator out, please give me a decimal approximation for the square root of 6. Just for graphing purposes. 2.45, thank you. So about 2.5. So I have, this is my parabola, and I'm doing an exaggerated parabola here. So that's the parabola. What the question is saying is, hey, I've got a rectangle inscribed in here. I want to find the maximum area. Not necessarily. Not for this one. Because my perimeter is not a set space. Okay? Largest area of the rectangle that I have. So what I need to do is figure out the shape. Now, the easiest way to do it is think about this coordinate here. This coordinate is x, and the y-coordinate. What is my y-coordinate? 6 minus x squared. If this was 2, I would plug 2 into there. If this was 1, I would plug 1 into there. What do I do if I know what x is? I plug x in there. My y-coordinate is that. That's my xy coordinate for that vertex. On the other side, it's negative x, 6 minus x squared. Okay. So what's the area of this rectangle? Well, one dimension is 6 minus x squared. That's the height. What's my width? 2x. Because x measures from here to here, that's x, but I have the whole length, so that's 2x. Does that make sense? Do you see what I get? Do you see where I'm getting my relationships from? Do you see where I'm getting my formula from? I don't know. It looks like x is at 2, but if I didn't have the dimensions at the bottom, x is just my distance. Oh, I go over, and then I go up to find my y. I don't know what x is going to be that's going to give me my best value. It might be 2.45 and have a really short one. It might be really narrow and tall. I don't know. Okay, but it's 2x across the bottom, 6 minus x squared on the top. Distribute. Area equals 12x minus 2x cubed. And when in doubt, take the derivative, set it equal to 0. So a prime is 12 minus 6x squared. Set that equal to 0. So 6x squared is equal to 12. X squared equals 2. X equals the square root of 2. And plug the square root of 2 into the equation and figure out what the area is, because that's what it asks me for. But that gives me my dimensions now. If I want to work it out, I take this, put it into here, because it's actually easier. Area equals 6 minus the square root of 2 squared times 2 root 2. Square root of 2 squared is 2. 6 minus 2 is 4. 4 times 2, 8 root 2. That's the area. I don't have any units, so I don't have to worry about units. No units are given. You don't have to give any units in your answer. That's the area. That's the greatest area possible. Now, I know you did work with this stuff in pre-calc, but what'd you do? You graphed it and found the maximum stuff off the graph. This will do it without it, and this will give you an exact answer, the square root of 2, rather than the approximation that you get off of your graph. Okay? And I will be looking for exact answers, because I have had students in the past go, oh, well, I'll just pull out my graphing calculator, I'll graph it, I'll do like I did in pre-calculus, and they get answers that don't match exactly as they should, because they're not exact values off the graph, and I have exact values. Because this is an exact value. Okay? Okay, find the dimensions of the triangle with the maximum area if the hypotenuse is 10. Ooh, hypotenuse is an extremely important word. Because if I have a hypotenuse, what kind of triangle do I have? A right triangle, because only right triangles have hypotenuses. It's only hypotenuse if it's a right triangle. That makes it muy importante. Which means that our area is 1/2 the right leg times the other leg. Right triangle. Makes it easier to figure it out. You can only do it that way. So here's what I want you to do first. See if you can figure out first and foremost what the length of the two legs are in terms of one variable. Okay, so probably the most difficult part is coming up with the correct equation that you're going to maximize or minimize. This one you want to find an equation for the area. That's not very hard to do. Problem is you need to be able to do it in one variable. So I know that this is a right triangle. If I call this x and I call this y, I can solve for y in terms of x. X squared plus y squared is equal to 10 squared. Pythagorean theorem, right? Pretty basic. Y squared equals 100 minus x squared. Y equals the square root of 100 minus x squared.
Let's go. I got that.
What?
Can you reduce it down to 10 minus 9?
No.
Why not?
Okay.
Because no.
Wait.
Okay. Now that we're done with my pet peeve. So the area is 1/2 times x times the square root of 100 minus x squared. Which I wish to take the derivative of. But before I take the derivative of that, I rewrite it as 1/2 x times 100 minus x squared to the 1/2 power to make it easier. Product rule. Derivative of the first times the second, etc. A prime. Derivative of the first term, 1/2. Times the second term, 100 minus x squared to the 1/2 power. Plus the first term times the derivative of the second term. Bring down the 1/2 power. Reduce the power by 1. Times the derivative of the inside. So a prime equals 1/2 times 100 minus x squared to the 1/2 power minus 1/2 times 2 gives me the -1. X times x gives me x squared. 100 minus x squared to the -1/2 power. Factor. What's my common factor? (100 minus x squared) to what power? Wrong. Smallest power that's in both. (1/2) is the smallest power. You always pull out the smallest power, right? When you have x to the 4th times x cubed times x squared, what do you pull out? You don't pull out x to the 4th, you pull out the x squared, the smallest power. You always, when you do a common factor that's raised to powers, pull out the smallest one, (1/2). Times, this has been taken out. When I take 1/2, take (1/2) away from +1/2, I get 1. This is now the power of 1. 1/2 minus (1/2) is 1/2 plus 1/2, which is 1. This becomes a power of 1, because I took out the smallest power. So I have here 1/2 of 100 minus x squared minus another x squared. Distribute the 1/2, so that gives me 50. And then 1/2 times x squared, (1/2 x squared, (1x squared) gives me (3/2 x squared). And what do I do with that? Let's send it easier. So that's all. Are we having fun yet? Okay. Yeah, how are we going to solve this? Okay, I need to pause for a moment because Okay, here we go. Okay, so if I have it equal to 0, if I rewrite this, it's actually not as hard as it looks, because this is 50 minus 3/2 x squared over the square root of 100 minus x squared equal to 0. Take the time to rewrite it. Now, it's not so bad, is it? Because what do I have? Where is my denominator equal to 0? And x equals 10. X can't be 10, can it? Because if my hypotenuse is 10, x has to be shorter than 10. Does it not? X has to be shorter than 10. Because the hypotenuse is the longest side in a right triangle. Nothing can be the same length as the hypotenuse, except for the hypotenuse. Everything else has to be shorter. So that one's out. So all I have to do is actually worry about where is 50 minus 3/2 x squared equal to 0. Let's solve that. So that gives me 3/2 x squared is equal to 50. 3x squared is equal to 100. Square root both sides now, just because I'm feeling lazy about it. So that gives me, or actually divide by 3. X squared equals 100 over 3. X equals 10 over root 3. Yes. No. And oh dear God, please. Let me have a moment about that. Actually, I don't want this on tape. So our other dimension, y equals the square root of 100 minus 10 over root 3 squared. And then you simplify that down. Okay, that's all you really need to do from this point. That's 100 over 3. 100 minus 100 over 3. Figure that out. Square root. It's not that hard to do. Okay.
Especially if we have our calculator.
Yeah, so you get 200 over 3. To deal with that. So, yeah. Y equals the square root of 200 over 3. So, is it isosceles? No. It's not an isosceles right triangle because root 10 over 3 and 200 over 3. No. They're not equivalent.
Yes. Yes. You got it.
Okay, we're done for today.